Okay, now we'll go and talk more about or in more detail about this particular mapping, which is called as delta q cross sigma map to q. Now please understand this table can be realized. ये यहाँ पे लिखा था मैंने previous year जब सिखाया था तो ये जो table है this can be easily realized using if else if construct like this. So this is what this table lookup would actually be implemented if I want to implement it into a certain device or a certain program. I will check what is the current state, what is the current input, and decide what could be the value of next state. Right? So this is some way of understanding. When I say I do a lookup, what it means. When I do mean a lookup, if it's a data structure which is like a dictionary in Python, I can do just lookup, no problem. But if it is not a Python dictionary, if it's just something like a C program, I could implement things like this. Okay, so there are different ways of implementing and understanding how operations of finite automata happen. Okay, fine. Now the next thing that we are going to discuss, what is there? We talked about this. That's why I'm not showing language of. So, so they actually jump onto DFA. Yet we need to understand what is DFA. So I'll just have my own slide in between. Now the next concept that we are going to attack or that we are going to represent or that we are going to understand is called as determinism. Okay. With respect to these devices, FA without output devices, what do you mean by determinism? Okay, so that is what a question that we are going to answer in the subsequent discussion that we have today. Okay, so we already know what delta does. So this function delta takes two inputs per se. One input is the current state. Okay, and the second input is, I should make it larger so that cannot go back. Okay, fine. So this delta takes two input. One is current state and the other is current input. This is these are the two things that this delta takes input. Now, since it's a mapping, it will produce a result. So this is how I suppose I'm calling delta function. Then its result would be the next state. Okay, that is what we expect. But what are the options that I have if, okay, if the table that I'm representing, every cell in the table, ये जो table में I'm just referring to this table, if every cell in this table is occupied by exactly one state, if every cell in this table is occupied by exactly one state, then I will always get this particular thing evaluated correctly. What if these cells, some of them are not occupied by any particular state? So I have not written any state in some of these cells. Okay. इसका मतलब क्या है? जब मैं इस टेबल में कोई सेल एम्प्टी रखता हूँ उसका मतलब ये होता है, for instance, if this cell is empty in state q1, when the input is 0, okay, when input is 0, I don't know what to do. That is what it means. I don't know what to do. That is what is the meaning of it. Okay, so I'll just tell you what can be the second scenario. So the first scenario could be, whenever I'm calling this delta function, the first scenario could be I call the delta function with current state and current input. I get exactly one next state. Second instance or second alternative could be, due to the way I have defined the mapping, these can be the three different scenarios that may occur. Okay. Second scenario that may occur is, if I'm in a current state and I provide the current input, I may just get epsilon or I don't care because I don't know what to do in that particular set. That particular cell is empty. That is, this particular pair, current state, current input mapping, it does not have any transition defined. It does not have any transition defined. Okay. Now then third alternative that can happen is, in physical devices or physical physics world, I should say, physical existent world, I should say, we never see that when we are in a particular state and a particular input comes, we end up in multiple states. For instance, if I have water and if I heat it, I get vapors. Okay, if I have ice and I melt it, I get water. If I have water and I freeze it, I get ice. Okay, there is always a 1 1 on 2 kind of mapping. But what if I have 1 to many mapping? Okay, so this particular mapping was what kind of a mapping? 1 to 1 on 2 mapping, because every pair had exactly one thing defined in the table. So 1 to 1 on 2 mapping was there. Here it was, I should say, a mapping where some of the pair there was no thing defined in the other side. यानी ये कौन सा type का mapping होगा? Into mapping होगा. Again, there is no one-to-one correspondence maybe. Okay, so one-to-one and on-to mapping, ये जो restriction है ये यहाँ पे नहीं रहेगा. In the third way, what we are saying is next states होंगे, एक से ज़्यादा states होंगे. That is, when I am in a particular state and a particular input, I will end up in multiple states. ये multiple state physical world में हमको इतना नहीं दिखता, लेकिन you can think of certain scenarios in computation where it is more natural to have this kind of mapping, one to many mapping. One current state and current input is mapped to many next states. Okay, so it's a one to many mapping. Again, it can be onto or it can be into. If it is onto, then we will not have any epsilons in this in the table. Okay, there will be either one single state or multiple states, right? Do you understand what exactly we are talking about here in this particular three scenarios? The scenario number one is called as deterministic scenario. Why it will be referred to as deterministic? So I have actually ticked it, and I will be crossing the other two scenarios. Okay, the first scenario is called as a deterministic scenario because when I am in some state and I see some input, I know exactly what is the next state. Okay, that means I can determine the device behavior using the transition function. Why it is possible? The reason behind it is possible is because every pair of current state current input, there is exactly one next state defined. अगर exactly one next state defined नहीं है तो दो अल्टरनेटिव वे हो सकते हैं. एक तो नेक्स्ट स्टेट डिफाइन ही नहीं होगा या वहां पे मल्टीपल नेक्स्ट स्टेट्स डिफाइन होंगे. तो ये जो दोनों अल्टरनेटिव है ये डिटर्मिनिस्टिक नहीं है. द फर्स्ट वन is the only alternative definition of delta that can give you a deterministic behavior for your finite automata. Now, if finite automata is showing a deterministic behavior, it is referred to as DFA, deterministic finite automata. So, the set of devices that we define, this particular device, deterministic finite automata, is shorthandly represented as DFA, deterministic finite automata. So today we saw the definition of what do you mean by determinism. When does a finite automata without output shows a deterministic behavior, and how do we refer to FA without output, a deterministic finite automaton? So a deterministic finite automata by its definition is a finite automata that shows deterministic behavior. Okay, how to write this in the mathematical definition? In the mathematical definition, the only change in the definition of FA that we saw and deterministic FA is that the delta function for FA now is restricted to be 1 to 1 onto mapping. That is, it is a total function. So whenever delta is a total function, that is, it is showing 1 to 1 correspondence and onto kind of mapping, then the device becomes a deterministic finite automata. ओके, सो व्हाट इट मीन्स इज हमारा पुराना वाला जो एफ ए का डेफिनेशन था, इस डेफिनेशन में ये वाला जो चीज है इसको हम लोग एक एडिशनल एट्रीब्यूट अटैच करेंगे. And that additional attribute will be of being defining total function. And when I attach this particular attribute to it, this finite automata turns into this finite automata turns into a deterministic device. Okay, so I'm not writing the entire word like this. Sorry, I use this guy. This turns into deterministic device. Okay, so what do you mean by the word total function? By word total function, I mean that the mapping that we are defining. So what mapping we are defining? Q cross sigma. This mapping we are defining between to Q. This mapping is showing one-to-one correspondence, and it is an onto mapping. So if you remember a few lectures back, I showed you what do you mean by one-to-one correspondence. That means every single left-hand side of mapping has a mapping there on the right-hand side, only one. So एक आप प्री इमेज से पिक करोगे सेट से, और एक आप इमेज से सेट करोगे, तो दोनों में वन टू वन करस्पॉन्डेंस है, एक का मैपिंग एक के साथ है. एंड देन ऑन टू मीन्स व्हाट, जो पार्टिसिपेटिंग रिलेशन है, ये जो क्यू रिलेशन है, एवरी क्यू इज इंक्लूडेड इन द मैपिंग. Okay, so that is one to one and on to mapping. Together, if a function is showing one to one correspondence and onto kind of mapping, it becomes a total function. And if a total function is there as a transition function for any finite automata without output, the finite automata becomes a deterministic finite automata. Now, when a finite automata is not a deterministic finite automata, a finite automata will not be a deterministic finite automata when, yeah, where is that slide? Here. When I am in one of these two scenarios. So if I am in one of these two scenarios, the device is non-deterministic finite automata or NFA. So a FA without output is non-deterministic finite automata when there is at least one pair of current input current state for which either the transition is not defined or there are multiple transitions defined. तो फिर से बोलता हूँ, FA without output is defined to be a non-deterministic finite automata when for at least one pair of current state current input, either the transition to next state is not defined, यानी epsilon है next state, या for one pair of at least one pair of current state current input, I have multiple next states defined. Okay, what this indicates or what this means, we'll just take a snap of this and we'll just realize what it means. Just brought it over here. Give me a second. Yeah. So this was our device, which is a deterministic device, right? I know that. And if I make a copy of this device, just keep it. So this is my deterministic device. And if suppose I add a label, I'm just going to add one label here. I have a white color this. Yes, I do have a white color. Okay. So if I if I add a label like this, sorry. Okay, what happened? It's not actually moving. I wanted it to move, but it's not. Let it be. So you understand that this label one is for this particular arrow. So now instead of having one label like this one 0 1, this also has 0 1 label. What this indicates or what this makes changes into our table in my table now there will be one row which will be for delta. I think this is del in bracket q0 comma 1. Now instead of taking me to a single next state, it will be actually taking me to couple of states. Either I stay in the same state or I move to next state. What this indicates, so this is exactly how I have defined one of the transition. All the rest of the transition are same in both the device. This device is a DFA, and the counter device that we have over here, because of this single additional transition, has become an NFA. Okay, so that's the change, or that's the thing that I need to. Okay, I hope this particular thing is clear to you. So whenever I'm actually using, so what I'm trying to make you aware of is, whenever I'm trying to model my transition function, the transition function is a function that takes two arguments, current state, current input. The output of this function is going to be next state. Okay, if there is only one state that I give output always on a pair of current state, current input, then the behavior is deterministic, because I know from current state, current input where the device is moving. Okay, which happens on this left hand side device. I am in q0, I see a 0 input, I know exactly where to go. I am in q0, I see a 1, I exactly know where to go. Whenever we are talking about this device on the right hand side, I am in q0, input 0, I know where to go. Okay, so that part is deterministic. That part, or that particular partial function, is deterministic. But when I'm in q0, when there is input 1, so this is one particular call to function delta with q0 and 1. Now, if you see the outgoing arrows from this state on labeled with 1, there are 2. Since there are 2 arrows, there will be 2 next state that I can reach. I can reach q0 from q0 if I follow this path, and I can reach from q0 q1 if I follow this path. So now I can, sorry, this has to be a comma. Accidentally put a dot over there. Sorry for that. It should be a comma. Either I will be in q0 or I will be in q1. That is a choice that as a device I have. Okay. So this behavior that we are seeing in this diagram is referred to as non-deterministic behavior, and the device that shows non-deterministic behavior as far as a finite automata is concerned is referred to as non-deterministic finite automata. Now we'll have one more copy of this device. Okay, let's put this guy thoda upar so that I can have, okay, क्या कर दिया मैंने इसको size बढ़ा दिया, sorry. Fine. I have this guy over here, and now what I'm trying to do is, I'm trying to, how do I do this? I'm not sure. I can't cut things. Okay, I'll do one thing. I'll just use an arrow with a color black. I try to draw an arrow over this. Okay, so I can use highlight now. Okay, sorry. I didn't know I should use this. The highlight color is not black. Like, so I'll use the arrow and I use a larger line. Okay. Now possibly I can remove. So I'm trying to remove this transition. By the way, what I'm trying to do is I'm trying to remove this transition. एक सिंगल ट्रांजिशन गिवन पर्टिकुलर डिवाइस से मैंने रिमूव कर दिया है. As I told you, I'm not good artist as such, so my drawing skills are really ordinary. That you can also understand. But the thing that I want to make you aware here is what you need to understand. उतना समझ में आएगा surely. So suppose I am in state Q0 in this case, and I see an input 0. Okay? What will be the state in which I will reach? If you will see all the arrows which are emanating from Q0, यानी Q0 से बाहर निकलने वाले जो arrow है, वो जब आप देखोगे, there is no arrow taking you out of Q0, right? There is no arrow that is taking you out of Q0. तो इसका मतलब होगा, तो पीछे गया उसका रीजन है, I just am bringing this epsilon here. Okay, yeah. का मतलब होगा कि my next state is epsilon. It's not defined. I don't know what is the next state. This device is also called as an NFA. Okay. So does it mean that I always have to have multiple transition in initial state? No, this is just an example. What I'm telling you is in the entire definition of transition function, at least one transition can be there that has this property, these two properties. नीचे वाला दो property at least एक transition को भी होगा, ये दोनों property at least एक transition को होगा. If at least one transition shows any one of these properties, okay, your device is doomed. Your device is going to be referred to as a non-deterministic finite automata. So these are the two properties that at least one of the transition should show you these properties. I don't know why it's not coming. Okay, let it be. Guess I made my point. That's more important. Speed this up. I put another box, which is very ridiculous, but yeah, I'm not an expert in using this either. Huh? So I'm just trying to learn using it. That's why these jokes happen. This is what I mean. दो प्रॉपर्टीज है, ये दोनों प्रॉपर्टीज में से कोई प्रॉपर्टी उसने शोकेस करना चाहिए. It is not going up. Okay, let it be. It makes sense. That's important. So at least one transition in my delta function should show any one of these two properties. Then the device is going to be what? An NFA. So NFA shows these two properties. These are properties of NFA. The two at bottom. और जो ऊपर के दो प्रॉपर्टी, ऊपर का एक प्रॉपर्टी है, ये होना चाहिए फॉलोड बाय ऑल द ट्रांजिशन for the device to be a DFA. So proving that a FA is DFA is cumbersome. You need to follow the entire transition table and figure out that every pair of current state, current input has exactly one next state. Then the FA becomes a DFA. Okay. For proving something is an NFA is very easy because you just need to pick one anomaly in the definition of transition function that shows any one of these scenarios. Whether the current state, current input is not defined any next state, that is there is no arrow for such combination, or there are multiple arrows for a current state, current input combination. Right? So this makes the distinction between two of the three categories under DFA and FA without output. One we said was deterministic finite automata. The other one was non-deterministic finite automata. Now there is a third category which is called as NFA with epsilon